In this video, we will continue to talk about approximations, and we'll come up with another method that will actually allow us to demand a certain accuracy in our approximations. Let's start with the same exact problem as last time, approximating square root of 2, but now I demand that it has to be with a certain accuracy. First, I'm going to actually turn what I would like to approximate into a function to work with. So I start off with x being square root of 2, which is the thing that I'm after here. I'm going to square both sides in order to get rid of square roots. And then I'm going to move everything over to the left in order to get an equation. So this is now a polynomial equation where x being square root of 2 is actually a solution to this equation. Let's think about this graphically for a second. So if I were to now sketch the situation, what am I going to see? I have a graph of x squared minus 2, which is just a parabola shifted down 2 units. And now I see that my square root of 2 and the negative version of it is actually an x-intercept of this function. So x-intercepts are also called roots. They're also called zeros. But among other things, this is the thing that I'm trying to approximate. So notice that approximating square root of 2 has now become an equivalent problem to approximating a root or a solution to this equation. And graphically, that means approximating the x-intercept of this function. Okay, so this is what I just said. I would like to note here just the vocabulary. We use the words x-intercept or root or zero interchangeably as they all mean the same thing. Now, if I would like to approximate a square root of 2 being the x-intercept of this function, again, the best idea we had last time was the fact that a function or a curve is very well approximated by its tangent line as long as I'm close to the point of interest. And it's the exact same idea that we're going to take through this method as well. Function is approximately equal to its tangent line near the point of tangency. And in particular, function's x-intercept, which in our case is square root of 2, is really well approximated by the tangent line's x-intercept, again, as long as I'm somewhat close to the point of tangency. So my function's x-intercept is square root of 2. So now all I have to do is come up with a tangent line whose x-intercept then will be an approximation for square root of 2. Okay, so this, we know how to construct tangent lines, and we should be able to find an x-intercept of a line. So this is going to be our next task. We're going to pick an initial point, a point at which to construct a tangent line at, somewhere close to square root of 2, find an equation of the tangent line at that point, and then find its x-intercept. Now, first thing I'm going to do, because this is very nicely visualized with the graph, I'm actually going to sketch the situation first. I need to pick a point close to square root of 2. Well, I know that 1 squared is 1 and 2 squared is 4, so root 2 is somewhere between 1 and 2. 1 seems to be a good point, so 1 will be my initial first point. And that, so here I'm going to pick x equals 1, and I'm going to call it x0. It's my 0th guess, 0th approximation. I haven't done anything for it yet. And what's going to happen graphically is I'm going to construct a tangent line to my parabola at this point, and then compute the x-intercept of this line. Notice that my x-intercept line right here is really, really close already to the x-intercept of my function, which is the square root of 2. So I can already see visually that my approximation is going to be a very good one right after one step. Okay, so let me remind you that my function is x squared minus 2. And now I need to find an equation of a tangent line to this function at point 1. So for that, I'm going to compute the derivative, and I need my derivative at 1. So I'm going to plug in 1, and then I'm going to take the already equation that we've already used several times and plug all of this information into there. Okay, so what do I have here? My slope, I've just computed to be 2. x naught I picked to be 1. And y naught is, of course, the x coordinate that corresponds, the y coordinate that corresponds to this x coordinate. So I can just plug in x naught equals 1 into my function to get the y value. The y value comes out in this case to be -1. Okay, so overall, the equation of my tangent line turns out to be y plus 1 equals 2x minus 1. So this is the equation of the entire tangent line that I have on the graph. I'm interested in its x-intercept. So in order to find x-intercept, I'm going to set y to be 0 and solve for x. So what do we get? 0 plus 1 is 2x minus 1. And solving for x will yield x being 1.5. The square root of 2 is approximately 1.412. So this indeed is a fairly close value. The other thing that the graph, much like in the linear approximation method, is very good at detecting is whether the produced value is over approximation or under approximation. In this case, I can see that my tangent line's x-intercept lies to the right of my function's x-intercept, which means that my approximation will be an over approximation. Now, this is the exact same number that we got with the linear approximation last time. So how is this method better? Well, this method's main strength is the fact that we can repeat this process again with this as our new value. Okay, so my initial guess was x equals 1, and my approximation produced the next best approximation, which is 1.5. I can now go through the exact same process, but instead of 1 as the initial value, use 1.5. The construction will look exactly the same, but with a new point, and will produce an even closer approximation. Okay, so in order for me to do that, I will introduce a slight notation here. I'm going to call this guy now x1, because it's my first actual approximation produced by the method. Okay, and that's the idea here, is that now I'm going to take my point x1 to be 1.5, and I'm going to construct the tangent line at 1.5, compute its x-intercept, and that's going to be my next approximation of square root of 2. So please pause the video here and go through the exact same process as on the last slide, but with 1.5 as your initial point. And then also try to sketch on the graph what you think that will result in. Okay, pause right now, come back for the answer. Now, this is what you should have gotten as the result. So my next approximation here is 1.4167. Now, the actual true value is 1.412. So this is already up to 2 decimal places accurate with the exact answer, or with the decimal expansion of the exact answer. That's fantastic news, because once again, we can repeat this process again and again to obtain whatever accuracy you want, as long as the decimal places get fixed. Once they get fixed, that's the accuracy already attained. Okay, now let's take a look at what actually happens on the graph in this case, right? So here is where I have my function x squared minus 2, and the little circle indicates the point I'm actually trying to approximate, which is square root of 2, which is the x-intercept of this graph, right? So the method says, the way that we started is I'm going to start at 1, and I'm going to construct a tangent line at 1. Here is the tangent line at 1. So I went up to the function, constructed a tangent line, and then the x-intercept of this line is going to be an approximation of the x-intercept of my function, which in this case is root 2. So you can see how the red line intersecting the x-axis is really close to the function's black curve intersecting the x-axis. And I can repeat this by taking the red line's x-intercept as my next guess, okay? So the process never changes. Wherever I start, I go up to the function, draw a tangent line, compute its x-intercept. So let's look at the next iteration. There it is. So the next line was orange. So at 1.5, I went up to the graph, constructed the tangent line, and you can already see that the x-intercept of the tangent of the second tangent line is so close that I know I'm gonna have to zoom in further in order to even see where they're different. There you go. See how close the orange line's x-intercept is to the graph itself? It's pretty amazing that we got so close within just 2 steps. If I do the next step, I'm going to do the same thing again. I'm going to take the orange line's x-intercept, go up to the function, construct a tangent line. And here, the green, the new tangent line that is green, is already indistinguishable from the graph again. So in order for me to even see where it is, I'm going to have to zoom in. There we go, way, way further in, right? So this is already accuracy to what it looks like 4 decimal places. Newton's method is extremely powerful. The method will approximate very quickly and very well, okay? So just to be sure that we understand what's happening here graphically, let me put this graph in here. Okay, so this is my approximation. And now I just want to, again, remind ourselves that this one was our initial approximation x naught. We went up to the function, constructed a tangent line, and the tangent line's intercept was 1.5, which was our next approximation, x1. We then did this again, and this is what this slide is doing. So then we went up to the function again, constructed a tangent line, and that x-intercept is the next iteration, or what we would call x2. And you will keep going until you're satisfied with the accuracy that you're getting. So the general idea is that we will start with the value close to the root of the function, or the x-intercept. So this is the guy we're trying to approximate right here. We will construct a tangent line at our point of choice. We will find its x-intercept and then repeat the process, okay? So graphically, again, we will go up to the function here, construct a tangent line at this point. The x-intercept of that line is our next approximation. So let's call this one x1, and then we can do it again. So then using x1 as our point, now I go back up to the function, construct tangent line. My next approximation is going to be x2, and so on. And you can see how I'm getting closer and closer to my point of interest, which is the x-intercept of the function itself. This is what it looks like on a graph. Let's try to derive this algebraically, because we should be able to go through all of the steps in a more general setting than with particular values, and hopefully come up with a formula that we can just use over and over again. So I have to construct a tangent line at that point, and then I have to find the x-intercept. So the first 2 steps are to construct a tangent line using a familiar formula. X-intercept is to set y to be 0. And then we're going to have to solve for x. This is what I get as a solution for x here. Make sure you actually follow through the steps to see how they worked out. And you will notice that here I replaced my y naught with the function value of x naught, and I replaced m with the derivative of the function of at x naught. This way, this entire expression contains only my initial point x naught, my function, and its derivative. So if you give me a function and a point, I'll be able to find the derivative, compute the function value and the derivative value at that point, plug everything into this equation, and get the next approximation. So again, because we will be iterating through this method, this is what we will be calling x1. But then we can repeat this process. So with x1 in mind, I can repeat this again, except for I will be plugging x1 into here, and the algorithm will produce x2, and so on. So in general, and what I'm going to write is the most general description of this method, we can write that xn plus 1, so starting with some xn like x3 or x4, I can produce the next value, xn plus 1, is the value, of xn minus f of xn over f prime of xn. And this is the formula that is known as Newton's method of approximation. For Newton's method, one can ask questions that are based on the graphical understanding of the method or algebraic understanding or carrying out of the algorithm. Let's take a look at the graphical question. So here's a function that I have. So clearly the curve intersects the x-axis in 3 different spots, A, B, and C. So these are the x-intercepts or the roots that I might want to approximate. And the question asks, if I start at this point P, which root am I going to approximate using Newton's method? So thinking back as how the tangent lines get constructed, let me go through the first one here. So starting with this point P, Newton's method goes up to the graph, finds a point on the curve, constructs a tangent line, and uses the tangent line's x-intercept as the approximation for the x-intercept of the function itself. Clearly, here, the tangent line's x-intercept is really, really close to b as the root, right here, the little point b. And so proceeding with iterations of the method will only bring me closer to root b. So in this case, it approximates root b. I leave the other two examples for you to go through using the exact same logic. The second part of this question asks more broadly, because I have three roots, what if I'm after a particular one? So for example, what if I want the method to approximate root A? Where am I picking the initial values from in order to guarantee that my method will come towards root A and, for example, not root B, like it did in this case? Okay, so here you have to think about how the tangent lines get constructed. So in order for me to approximate root A, it means that the tangent line that the method will build has to sort of point toward root A. So notice that if I do tangent lines here or anywhere here, they will point toward A. But once I'm past this hump, this peak, my tangent lines will now start pointing to the other side, and I will be approximating some other roots. So for the first part here, it looks like past this point is where the tangent lines will diverge from A. So to approximate root A, I have to be somewhere between, let's say, minus infinity and this point right here. So let's call it minus 1.6. Okay? Using similar logic, please think about what are the intervals for your choice of x naught that will land you near root B and near root C. Now, this is one of the key things about Newton's method, is the method doesn't care which root you're trying to approximate. The method will approximate the root that is somehow closest to your initial guess. So in general, sometimes Newton's method fails altogether. We will think about this algebraically and graphically as well. Let's take a look at this general formula that we derived for Newton's method. When is this going to be non-computable, or what can go wrong in this formula here? Well, the thing that go wrong usually involves denominators of some kind. So the thing here is that this thing on the bottom, the derivative at xn, cannot be 0. Because if it's 0, I'm dividing by 0, I will not be able to carry on the calculations. So this cannot be 0. So this means tangent line can't be horizontal. The other failures of the Newton's method are better explained using the actual graphs. So this is our first case. Let's actually just graph this situation. So if I'm trying to approximate some sort of a curve right here, and I pick my initial guess to correspond with the point on the graph where tangent line is horizontal, the next step in the method is to compute the x-intercept of this line. But it has no x-intercepts, so the algorithm will stall. This is one of the failures, the horizontal tangent line. The next failure would be an interesting situation like this one here, where I pick x naught, I go up to the function, construct myself a tangent line. Let's say something like this. Let's pretend it's tangent. This is my next approximation, and the method will repeat itself. So it will go up to the function, find a point, construct a tangent line. Well, that's unfortunate, because now what that means is the method will just get stuck in a cycle, right? It will alternate between these two values because that's where the tangent lines will always lead it. So sometimes the method can get stuck in a cycle. This is a 2-cycle. Newton's method can have cycles of any length. So you can come up with functions and initial guess that will lead you to a 5-cycle, 7-cycle, any choice of cycle. So this is the second way in which it can fail. And the last way in which it can fail is something like this. So again, let's try to actually construct a tangent line and see what happens here. So for this choice of x naught, I'm going to go up to the function, construct a tangent line, take my next x-intercept as the next approximation, go up to the function, construct a tangent line. Well, that's not looking very good because look, the x-intercept is actually at 0 here, but my guesses get further and further away from this, right? So this will be x2. Get further and further away from my actual function's x-intercept. So in this case, what happens is because the curve is so flat, the actual approximations will diverge to infinity. So remember that I mentioned already that Newton's method is very fast, which means that it will give you the desired accuracy, a very good accuracy, very high accuracy, after only a few iterations. But the failures and our graphical previous example do suggest that when you're picking an initial guess, you have to pick it close enough to the root that you're actually trying to approximate. And you also have to keep the shape of the curve in mind. Otherwise, you might get stuck in you might end up in one of these cases where the Newton's method actually is not able to proceed.